Okay, so we have 6 panelists today, and I'd like to introduce our panelists today. Let me introduce Wilfried Haensch from IBM, who is the right now used to be a manager. Now he is relaxing a little. And let's welcome Wilfried. And let me introduce our own Professor Vivienne Sze from ECS. Let's welcome her. And here, Professor Daniel Sanchez from ECS, MIT. And Professor Rafael Jaramillo from MIT, DMSE, Material Science Department. And here, Mr. Andreas Olofsson from DARPA. Let's welcome him. And last, here is Jennifer Rupp from Material Science in MIT. Okay, could you switch the screen? Okay, let's have an exciting discussion. So all the questions that I got will be here. I picked 2 questions out of many questions receiving, and we create some important question here. So let's take a look at the question here. Okay, let's discuss about the question from the audiences first. Okay, we're talking about spiking neural network versus non-spiking neural network. What is your opinion about these 2 different types of neural network, and what could be the future of these neural network? Can we start with Wilfried?
That's a very loaded question.
Yeah.
So I think spiking networks are very intriguing because they look like what we see in biology. But from a technical implementation, I think spiking networks are looking still for an application where they are useful.
Okay, Vivienne? Oh, that's too short.
So I would echo what Wilfried said. So I think for our research, we probably start from the application standpoint and move backwards. So as a result of that, we primarily focus our own research on the neural network space as opposed to spiking.
And Daniel?
Basically, I echo exactly what Wilfried and Vivienne said. Let me just add that there was at the beginning of this workshop, a very interesting presentation on how all these how the brain is really not a matrix multiply accelerator, and maybe it's not that you want to implement spiking neural nets, but the concept of having time or exploiting time in the computation of these networks. And how it applies to other styles of logic, let's say race logic, right? There's a lot of interesting recent work in this topic. So I think it's not necessarily spiking versus non-spiking, but how to incorporate time into to make these systems more efficient.
So,
I have a follow-up question. There was a chart presented today that had 4 quadrants: spiking, analog, spiking, digital, and there was IBM 2.0 on the digital spiking corner. So there is experience with spiking networks. And I wonder, I'm interested in Wilfried's answer to the existence of that chip.
So a couple of things. True North is not a training chip; it's only an inference chip. The energy efficiency from True North is not coming from the spiking; it's coming from the sparsity of the weights, how the weights are implemented there. Spiking is used to get some benefit in the communication. So in this respect, it's really not a bona fide spiking networks.
Rupp?
I think it's interesting. We're sitting here in brain and cog, and I could be mistaken, but I think most of us are electrical engineers or physicists, right? So in some sense, there are probably 100 people in this building that are more qualified to answer this question than I am. But this gets to a point which I'm sure will come out, which is that we're really talking about neuromorphic computing, which is brain inspired, but we're not doing neuromimetic computing. None of the people today are really focusing on that. So in that sense, I'm going to sort of dodge the question by saying that spiking is really getting at a completely different question, which is, what comes next? What's going to be the electrical engineering challenge 20 years from now? It's too close to neuroscience now for EECS to really sink our teeth into it. But it is an interesting instance of asynchronous computing. So if you think of it that way, it allows you to decouple processes in different parts of the processor, and perhaps there's some progress that could be made thinking about it in those terms.
Okay, Andreas?
So I manage program labs at DARPA, and there were a lot of people doing analog computing, and including spiking neural networks. And I would say that beyond the application, also the huge hurdle of getting it to work in a reliably, in a manufacturable sense, and the effort involved in creating each circuit. With the digital, we kind of write our little code, press a synthesis button, to get something fairly optimal, because we work at the Boolean level. In analog, we don't have that, so you get very, very expensive effort for every data point. So we end up getting a very sparse graph of maybe 3 or 4 data points. And of course, today, you write your TensorFlow or PyTorch network, right? And then you deploy it to a GPU or a CPU, and you innovate very, very quickly. So whatever you're comparing to, the alternative has already moved forward, like more, right, by 1000x. So I think that's one of the challenges we found. We were always comparing things like MNIST that was 20 years old and was irrelevant. So interesting, but it's got to move at the speed of everything else.
So if you receive the proposal, one spiking, one non-spiking, what would you choose?
Neither?
Okay, and quantum.
It's got to be application driven for sure.
Okay, can I ask a quick follow-up?
Yeah.
With your perspective, are there still outstanding applications for which you're waiting for the right spiking implementation to come along?
I would say something close to the sensor. If it's just linear algebra, that's not very interesting. If it's something that's tightly coupled to some kind of stimulus, I think that could be interesting.
Okay. Jennifer?
Yeah, I think that's a very interesting comment. So, adding to that is we discussed analog computing, but also do we think enough about hybrid type operations? So can actually a part of the analog computing also sense in parallel what's going on in the environment? That are, for instance, questions that I think from a material hardware level and, let's say, operation principle are quite attractive to look at. And that one I would actually agree very much with you. And these questions are not answered yet, I think, from material hardware.
So may I ask about IBM abstraction? So is there 2 different activities going on in parallel, or anything like way more onto spiking or non-spiking?
What is the question?
My question is the research activity in IBM research regarding that direction.
Oh, spiking versus non-spiking?
Yes.
We looked at both. And I think based on our experience with the spiking, we think spiking is just not there yet. We're still looking at it. It's an interesting solution, but as I said, it's not clear what application you will run it. Yeah, we'll leave it like that.
Okay, thank you. Thanks for the answers. And let's go on to the first question that I was supposed to ask. Okay. This theme is workshop on AI hardware technology 10 years out. So it's a great question for this workshop. So revolutionary AI hardware 10 years out. What is in it? What is the highest priority to AI hardware development for the next 10 years?
Well, it depends where you stand, right? If you're in a university, you want to look at new ideas. If you look at a person who wants to make money out of it, then you need something that works reliable. And usually there's a 12-year difference, right? So if you look at a 10-year time horizon, then you get a different answer from me than from my academic colleagues. So I think, whom do you ask? What?
Who's asking you?
If you ask my opinion, right? I want to make work what we know is feasible right now, right? And we have ample evidence that these analog solutions are feasible. Whether they really hold water, that's a long way to go still, right? So.
So what is the biggest challenge then now in analog computing?
I think the biggest challenge is really two things. One thing is to find a manufacturable material solution. That's one thing. And the other thing is to build a system or build an architecture that is software compatible with what we have right now, right? Because if you don't have that, you cannot go anywhere. This is if you stay in the commercial space. Right? If you rip everything apart and you need a complete new software infrastructure, there's a huge barrier for inserted into the commercial space.
All right, thank you. Vivienne, what do you think?
All right. So I think, obviously we're in the age where there's going to be more specific hardware, for example, for AI. I think one of the big challenges is that when you want to be domain specific, you don't want to be too narrow at the same time, right? So obviously it takes us much longer to make new hardware than it takes for people to make new algorithms. So I think one of the big challenges moving forward is how do you build efficient hardware but still make it flexible so that you can support future algorithms. And obviously most of the time when you introduce flexibility, it comes at a cost to efficiency. So I think understanding where to draw that line is important. I think also coming from an application standpoint, it's also important to understand the application well and not just look at it like a workload, because it will also evolve, right? So people in that space, let's say working on neural nets, let's use as an example, there are certain things they're trying to achieve depending on what application that they're looking at. So it's important to not just look at it like a fixed network, but how this network might change in the future as well. So having some notion of where, as these are like kind of dynamic workloads that will evolve over time, and so trying to predict how it will go forward is important. So flexibility and also understanding of the application is important.
Really understand application.
Yep.
Okay, thank you.
Yeah, so I would say one of the main things that we need to think hard about from the hardware side is, that over the past 5, almost 10 years, basically GPUs and data parallel hardware have been the enabler of deep neural nets and the current revolution in deep learning. And one major concern is that this hardware might actually restrict the kind of algorithms that get studied and developed and ultimately make it to the public. And it would be really constraining, right? If we started focusing on only implementing, there's basically a feedback loop here where we only focus on accelerating the algorithms that are already developed, that are already targeting the previous generation of fairly restricted hardware. And so, even things like sparse neural nets, attention networks, and so on, there is a lot of trade-offs that are being made to try to map this efficiently to current hardware. So I think that one really important part of hardware evolution in the next 10 years is really generality, is to figure out starting from the algorithms, what is the right thing to do, and especially one thing that we're very good at doing in hardware is to take a problem that is not algorithmically efficient and accelerate it to death, right? So, in graph algorithms, for example, you can do an accelerator for a very inefficient algorithm that processes the entire graph per iteration, right? But then there are algorithmic advantages that will make the algorithm hundreds or thousands of times more efficient on conventional hardware than what you'd have in custom hardware, right? So I would say, the key thing is we need to make sure that this hardware does not fight with the algorithm, with algorithmic efficiency, and that it helps, develop new styles of algorithms rather than constrain the development of it.
So what could be the best way to expedite or promote the collaboration between a software engineer and hardware engineer? What's your opinion?
It's complicated because domain experts don't really want to think about hardware, right? And so once you sit down with a domain expert, you can start finding ways of making that algorithm efficient. But typically, that efficiency comes from completely different principles.
Usually it works like this. You provide a piece of hardware, the software people go at it and see the limits, and then they get creative and work within the limits, right? So I think it would be interesting to find a model where you don't have to wait till the hardware is there, that people think out of the box and address the limits, right? Because this could also guide an improvement of hardware development. But this is not how the world works right now.
Right, exactly.
Right? The GPU is a typical example, right?
So precisely the problem is that then, as hardware designers, we'll look at this software that is playing within the limits and say, well, this is great. This is completely sufficient to do what the software people want to do. Let's just restrict it a little bit more. See where they can keep, doing 4-bit integer multiples. So.
Yeah. So, Rupp, you have a.
Yeah. So. I guess you said 10-year. If I could answer the question of 20-year, I think one thing which emerges from the first talk and some of the questions is that we're missing the complexity of the brain, and we have ways of capturing that, like fan-out numbers and precision, right? 16-bit for your brain, something like this. Totally impossible for our neurons, that we do in oxides or. So I think that there are people, again, in Brain and Cog who treat complexity as its own science. And we would do well to learn from them. So for example, maybe 10, 15 years ago, there was a hype wave around self-organized criticality in complex systems, things like cellular automata. But I think that there's a lot of useful ideas there where we can stop trying to analyze every single little device and figure out what emerges when you couple n devices and then scale n. Another area where this could be very useful is borrowing some ideas from quantum annealing. So how do you optimize in materials? Right? Inference is not a hard problem, it's like a solved problem. Right? It's optimization and training that is consuming all of our energy resources. So can we do that in materials? There have been efforts at, say, quantum computing that went down paths of simulated annealing, and that was considered not real quantum computing, and that's fine. I'm not here to talk about quantum computing, but there's a lot of interesting optimization within materials, where if you take a systems level approach, you could say, well, how do we define the topological and boundary conditions that would cause a system to evolve toward the solution? And right now, when I work on neuromorphic computing, I'm still thinking IV curves, which is fine, right? I'm a material scientist, but it seems like that's what the field is missing. That's what this room is one of the things that would really take us from where we are today, or across like your shirt, the arrays, right, to really understanding what are the profound what profound advantages in energy saving do we get due to massive advantages of scale and connectivity.
Andreas?
So the first thing I would say is I'd like to throw the picojoule per watt metric out, or gigawatt per watt, or picojoule per operation metric out the window. I think that's a disservice to the field of innovation. So you should look at useful work, right? And not normalize to some linear algebra, DGEM computation. So I've seen way too much of that. And I like Neil's statement that maybe we need a do-over, right? So right now we have 70, 80 years of people setting up departments around computer science and MIT, and you're either in that department or another department. If you're going to reinvent the way we compute, then it's going to be a collaborative effort. That seems very, very complicated. It breaks with how people get their PhDs, are domain-specific expertise and so forth. So it's a profoundly hard problem that requires collaboration across disciplines. But I would say one thing that I'm sort of excited about, that Vivienne mentioned as well, is that there's always a cost flexibility. That's basically what I've been, like on a personal level, been doing for 20 years now, designing commercial chips. And to quote one of my colleagues, like rearranging the chairs on the Titanic, the ship is going down, just doesn't really matter what you do. You can trade off a little bit of flexibility for performance, doesn't really matter. So I would say 20 years from now, I'd like to see something that is not even configurable in the field, but morphs in the field, either chemically or mechanically or by some means where, imagine a bag of, I'm really going to go out there now, but a bag of molecules, right, that somehow evolved with time, right, for a certain application. I don't see any other way to fight this flexibility versus efficiency battle that we're kind of stuck right now.
Yeah.
Yeah, so, I mean, being a material scientist here, putting that cap on for a moment, I think I have two dreams for in 10 or 20 years. The first one is on a larger scale to see far more hybrid devices, not treating like sensors in a traditional way anymore that they have to sense, but be maybe much more integrated with some other type of units. So questions like, can a battery also have a part of a sensing function as well? Can a processor also have these functions? And I think this would give far more opportunities, and it stems currently that these disciplines are still very separated. If you go to a classic material science conference, you have a sensing symposium and you have a neuromorphic computing symposium and you have, let's say, some other domains. This has, for me, to intertwine more, and there needs to be more crosstalk to design this new chemistry and physics. And on a smaller length scale, thinking about these physical principles, what are the dynamics, what are the defects that are involved in these phenomena, and what is the cost of energy that I have to pay for those, to gain more clarity for the neuromorphic computing part, but also for the other domains in AI, what is possible here. So that's, I think, the two parts that excite me quite a bit to explore together, with everyone else here in the room and industry in the next 10, 20.
Point of view from material scientist the next 10 years. And this is such an important topic. And do you have any related question from the audience on this thing next 10 years? Jean, you have some?
I think all these things, we're kind of in this weird mode where we got here through a self-organized process that nobody controls, which is the whole Moore's Law loop with economics, which is the input factor. And so it's not clear to me we can go anywhere else without another input factor from the economy really driving us. Now, we don't know what that is yet, so we got to do research and try to find it. But I think kind of like, it's very difficult to step back and say, okay, we're going to like invent a new paradigm now when you have to have economic loop in there, right?
Yeah. So any?
I'd say governments played a pretty important role in the last 70 years in kickstarting things, at least, right? Not sometimes getting it over the valley of death, but eventually commercial has to take over. At the start, I think government has a big role. And but the question is, how many billions can you push in before you?
Yeah, I mean, this could get philosophical, but I mean, obviously, right? I mean, nobody's going to invest that far out in time except for the government, right? I look at the, it's kind of interesting. government application which could be justified by society was a defense one for semiconductors, and it just so happened that the same parameters for that investment also were valued in the commercial domain, which is extremely rare, right? So, you know, what society will pay for going forward, it's not actually clear that we'll find another economic loop anytime soon. So, for example, you know, anthrax can be very important for a defense application, but there's no commercial spillover, right? So it's just I think these things are a lot harder than we think because we've been in an easy paradigm.
I mean, some might argue that AI is in kind of the same space right now, where China, Korea, Europe, the U.S. investing at the government level, investing enormous amounts of money in this broad field of AI. Not necessarily AI hardware, but AI. And
That's just an application, though. That's no Moore's law, right? It's not a, you know, self-propagating exponential. Right?
So I think in many years of engineering, certainly CMOS, we know how to make a lot of progress if we have a modular approach. We define interfaces at different abstraction levels. We agree on defining this interface, and then we work at our levels with that interface in place. So it seems to me that to make progress on this, again, thinking on 10 years out, where we don't quite see the contours yet, we need to develop a similar modular approach and agree on some interfaces. But I don't see, looking at the presentations today, how to do this. I wonder if there are some suggestions.
Well, I disagree with that. Because if you look of an IV characteristic of a transistor 20 years ago, and you look at an IV characteristic of a transistor from a 7 nanometer node, to first order they look alike. And this is why this modular approach is working. Right? And but if you lift the lid and look in the pot, what boils, right? Even in the chip industry, the modular model is long gone, because there's such a tight interaction between technology, design, architectures, that it is you cannot look at these different levels in an independent way anymore to get the optimal solution. You can include something together that is suboptimal, and this might be okay. But if you want to have an optimal solution, there's a tight interaction between the different levels. In the AI space, what I believe, the coupling between the different levels is even larger, right? I think because the technologies will drive algorithms, algorithms will drive technology, algorithms will drive applications, and so forth, right? And I see this already when I look at the analog space, right? Digital used very, very successfully stochastic gradient descent, right? In all its different variations and forms. In the analog, it doesn't work because you need this perfect symmetric device, right? Now, no one in the world will create a perfect symmetric analog device, right? So what you have to think about, is there anything that we can do in the analog level that we can make it work? And the answer is yes, there are possible ways how to make it work. And this goes up the whole food stack. The other thing is you look at the enormous success of convolutional nets, right? And if you step back and look at how convolutions are implemented when you go in the analog space, that's a nightmare, right? The question is, can we do the same thing that convolutions do in another way? Right? That's an algorithmic question, right? To take advantage of the technology, but you cannot separate that stuff.
Well, but in some way, if I may argue this point, I look at, for example, Vivienne's presentation. She had a lot of block diagrams.
Yes.
Well-defined functions. I agree. The optimization of the blocks has to be done concurrently. So there's a well-defined interfaces, an understood function that is what each block does, and the system is constructed that way.
This is true for if you build on a digital architecture.
Exactly. So
yes.
To make progress, it seems to me, we need something like that.
Why?
Well, because
Because you don't want to
That's what
talk.
we think.
Because you don't want to talk to the other guys in the stack. Because it's a big problem. That's exactly the problem.
Yes.
Right. The software guys don't talk to the hardware guys.
Yes.
And the other way around. Right.
Yes.
When I'm working in the industry, I did work. I'm retired now. So, but I worked 30 plus years. Right. And how many times did I go to the design community and say, "What transistor do you like? Give me the same that I always have." Right? What would you do if you get this switch? Well, I don't know. Right? Give me what I always have. Right? Because they were so busy living in their layer, that they didn't see any value talking across the layers. And this has to change.
the progress has been staggering in works.
This is the nature of the technology. The AI stuff is a new beginning.
Yeah, to that point, there's actually business theory showing that in industries that are old enough, you go from vertical integration to horizontal back to vertical. There's no question vertical integration is where things are going to appear, which means that you get people together through the stack to work together. The problem here is I don't see the value at the other side, but that is definitely the truth.
No,
right?
no, see, this is already a fallacy in that argument, because when in the end game people work together on the vertical integration, they do that because they have to, because there's no other way how to make progress.
Yes.
Right?
Yes.
What I advocate here in AI space, they have to work together because they want to, not they have to.
No, I agree, except that usually you have to have some. So we've done this actually. I did this the last 7 years, and we didn't know the exact application. We didn't know the last market, but we did get people together vertically, and now we have chips coming out that are completely unique with new materials in them. But we kind of knew what we didn't know exactly what form, but we knew there was market value in a wide range of things. So like it made sense to march together towards that, even if it's 10 years away. See, here I have the problem that there's no marching orders. Like if you solve this problem, it's not clear what we do, right?
Well, is it an awful thought?
No, see, this is what the academic always says, but actually, if you go back and look at the invention of transistor, everything else, it was never like that. It was not people doing random stuff at all. So it does not work that way, even though over in academia, we love that because we could shirk all responsibility.
Don't talk about random stuff. I think if we talk in a very narrow picture of AI and deep learning, right? It's a very narrow picture because AI is much more. But if we only talk about deep learning, I think the problems that have to be addressed are very clear. And there are solutions out in certain spaces and in other spaces not. But the problem is very well defined.
So that's what we should be talking about, so go ahead.
Right?
What are those things?
All right, I can add something to this. So I think, in general, I think one of the motivations for our group, how we got into deep learning, was the higher level question I had. I worked in video compression before I came back to MIT. We have video compression behind most image sensors out there. If we really want something like deep learning or something like computer vision to be ubiquitous, you have to fit that kind of capability in the same area, energy, and cost budget in general as you would video compression. Right. So we took a look at both handcrafted features, which was the state-of-the-art at the time, and then deep learning that was up and coming. And even with just pure hardware optimization on both, just digital hardware, there's still a 2 order of magnitude gap in terms of energy. And so you're not going to be able to close that just staying at a digital architecture level. You really have to start thinking up and down. So we chose, just because of the area of expertise that we have, we chose up. So we co-designed both the algorithms and the hardware together, and there you can get another order of magnitude, almost 2 orders of magnitude savings to try and close that. And that's the motivation, because you actually want to deploy these in very cost-constrained type of application, like systems. You really have to look beyond just one layer of optimization. And you would see similar challenges if you go in the cloud too, because what they're limited by is also power efficiency. So if you want to have a lot more things running deep learning and AI, you need to be computing more efficiently, right? And that's also the motivation of going to domain-specific types of applications as well, right? So you have a lot more demand of compute, but because of the slowdown of Moore's law, you need to have more specialization. And so again, when you start talking about domains, you have to think about what is the definition of domain. You have to think of the application, you have to think of the algorithms. Otherwise, you're designing for today's algorithms, which might not be the future algorithms that you actually need, right? So the co-design, and as Daniel said, it opens up the space much more broadly to think of new architectures as you're designing the algorithms, and then vice versa. And there is a big motivating case because there's a demand for compute, and in the existing separated approaches, we can't deliver for that demand. It's limiting progress in that space.
We're already covering question number 2 and 4. So we're mixed. So let's.
I want to take a try at this is a question about interfaces. Right?
Yep.
So software and hardware, right? The ISA is probably the most famous interface that we have, right? Extremely successful. On the physical side, it hasn't been as good. So actually interfacing physical things, right? I mean, there's standards everywhere, and they tend to be pretty coarse. Things like USB, PCI Express, Ethernet, right? But as you get further down into the package, we really don't have a way of heterogeneously integrating things, right? And that is an enormous opportunity space for getting gains, right? So DARPA's been running programs there for 10 years now. Things like DAHI, trying to blend materials, right, to create really, really good RF circuits. Or like the CHIPS program, we're trying to cut, a monolithic die into tiny chiplets, each optimized, right? So you can imagine having a catalog of specific functions that then get bonded onto some kind of wafer to create the optimal function. But the idea of combining the best in breed, right, whether it's new memory devices or new transistors or new functionality, right? But for that, you need interfaces, right? And it doesn't seem like anybody can agree what those interfaces should be. Materials, electrical interfaces. But if you could, I think there's a big space.
Then do you think in government agencies there is a specific effort to combine this hardware and software activity together?
So when it comes to standardization, we can't do anything, right? Like the government can't set a standard, right? It's got to be industry driven or bottom-up driven, right? So we can certainly, like I said, we have a bunch of programs. ERI, right? This Electronics Research Initiative is $1.5 billion, investing in computing, hardware, new software, and I mean it's got a bunch of really great programs, but I would say it's still fairly near term. It's maybe 5 to 10 years out. Beyond that, who knows?
Right? No, 10 years, at least 10 years. Yeah, then let's make a smooth transition to, I think, number 4. Okay, achieving low power, small scale AI hardware will really save the industry facing the limit of Moore's law. Daniel, you want to start?
Low power, small scale.
Yeah, ideal AI hardware comes out.
What does that mean? Like,
Is there a question mark behind the question mark?
Oh, there's a question mark. Yes. I sent you yesterday.
Are you asking if like small scale AI is going to drive solutions beyond Moore's law?
Beyond Moore's law.
What is small scale AI?
Yeah.
And do you mean what's small scale? You mean like IoT devices, or what do you mean by small scale?
So ideal AI hardware that doesn't consume a lot of power like a CMOS, it can go, you can enter many.
Oh, this is a question that is half-baked cake, right? You always can make low power if you run it very slow, right?
Okay, let's take that one. Let's say you have AI hardware.
So what?
Then we have Windows.
Did you make this question up?
Jeehwan, you've got a revolt on you. We're going to have to define this better.
But if you don't like this question, but you understand what I'm asking.
The answer is run lots of processors so each one of them can be slow and low power.
So ideal hardware comes out. We dream of some AI hardware. We work on it. So we really ideal AI hardware comes out. How can this be related to the industry that's facing the limit of Moore's law?
I mean, for me, Moore's law, the manifestation of Moore's law is that every gadget that you buy, right, has hardware, has some microchip in it, right? And whether this will be true with AI-related hardware, I'm not sure. Right? There are people out there that say that will be pervasive, right? I'm not quite there yet. So it has to be seen what AI can deliver, but we have to understand, right? We use AI in a very kind of nonchalant way, right? All the popular stuff that we talk AI right now, this is all deep learning. And deep learning is a very, very small part with very, very, actually very tight constraints on it to make it work, right? So 10 years from now, when we talk about AI, there might be completely something different, right? And then this question might be more relevant. I don't know.
I mean, it is the end of Moore's law is placing a lot of constraints on how compute capabilities evolve. But I mean, just building on what Wilfried is saying, I hope that in 10 years, right, the algorithms have evolved and so have the hardware platforms. And I mean, a different way to look at this is, we have a great existence proof of doing intelligence within 20 watts. How is current fabrication technology failing to get us there, right? And so one of the things that is a constant in at least in computer systems and computer architecture is that we love to focus on compute, right? It's in the name, right? We love it, right? It's all the CPU, building cores. Here, a lot of talks have dealt with how to do matrix multiply accumulates really fast. But in fact, if you compare silicon fabrication technology, at least where we are now, and the brain, the largest difference is in the interconnect and in memory, right? So the brain is great at doing memory at very low power and in a distributed way, which is something that in silicon we have not yet figured out how to do. To get cheap memory, we end up putting, fabricating it in a completely different process and putting it far, far away. So memory accesses completely dominate energy. And then the capabilities of the brain interconnect are far, far beyond what we can build in silicon today, starting from the very fact that we're limited to these substrates. But even when you look at systems like what Max has presented early in the morning, it is 3D, but it is 3D in a very structured way, whereas the brain is very good at doing very dense and very unstructured and long connections. And so I wonder whether there's some device level progress in that style of interconnect that might enable more connectivity and new algorithms.
I would really second that. The von Neumann paradigm is something we can wrap our minds around, right? And we can design these elements, and it provides motivation sometimes when we don't know even what the application is, right? You can't look at a transistor in CMOS and integrated circuits in the 70s and envision the cloud, or a few people can, right? But you can pursue that direction. And the challenge now is that the brain provides us our inspiration, right? But the brain is too complicated for me to understand. So one thing which I think could help focus this question, right? What am I supposed to look at a lithionic device and see some future application? I mean, I'm incapable of that, right? And I don't think too many people can. Here, Jenny. But I think we're missing an element of modeling, right? So for example, we have Kirchhoff's laws, we have SPICE. How do we model anything that a device engineer, physicist, or material scientist can dream up? How do we model the emergent behavior when you wire 10,000 of these things asynchronously, say? We don't have software for that. That's actually a big computing problem. You could use AI and deep learning to model such things, and that's pretty, neat application. And try to see emergent behavior, and always have the power in the denominator, right? So you're always modeling power, because that might be the way to discover, right? We have to model these systems at scale, much more than individual, IV curves and cross-point arrays, and let those outcomes tell us what sort of physical behavior to look for, right? Because the IV curve of the transistor, it doesn't speak by itself, right? It doesn't tell us what the application is. Again, this comes down to talking, right, across different levels.
All right, so we have 10 minutes left. So we have 2 questions left, but I would do the question from audience. So is your question, how will AI hardware be programmed for particular task? I didn't understand yet. Could you explain a little more about your question?
Yeah, like what language and what language features would be appropriate for interfacing with AI hardware?
No language.
It seems clear that the language has to be able to handle a lot of parallelism. So
Yeah.
that the parallelism that's presented by the AI hardware can be exploited.
Do you mean what language? What is the context? What is the context of your question?
Programming language.
Programming language.
I'm an applications person, and I want to apply AI hardware to an application that I.
So you want to build an application that does some stuff for you.
I'm building a self-driving car.
Yes.
I want to know, and I have to program write the software to do it, and it's going to use some AI hardware to to do scan the scene, identify obstacles, all the things that a self-driving car has to be able to do.
I mean, ideally, the programming language would be you stick the device in the car and you take it for a drive.
Yeah, the problem is that even though Elon Musk says that in the end there's going to be a neural net taking images and controlling the steering wheel, will you get on that car? I mean, it is.
Well, that's the way my kid learned to drive, right?
Yeah, and humans are
gradually I'm willing to
extremely
let
bad
him
drivers.
drive the car when I'm in it.
Right. So I mean, I think the great argument is that you can put enough sensors that cars can become better than humans. But I mean, we suck at driving already, right? Like it's pretty low bar. I think there's an interesting question there, which is what's the interface between some of these deep learning based techniques that are much more about training models and then just use more data to get more accuracy kind of AI applications and more programming or classic AI applications, if you will, right? Is there something in the middle? And these seem quite disparate right now. It seems though that there should be some interest in continuing. Right?
There are. I mean, now there are lots of platforms out. You have jockeys for everyone. Right, TensorFlow, PyTorch, you have whatever is out there. They all help to abstract so that you don't have to write real code, right? But I don't know whether this is the question that you ask. It's regarding to the self-driving car.
He's not happy.
It is.
There's a question.
Yeah.
Okay, there's a question. Okay.
So I'm going to say something as one of the core organizers here. So just one thing I want you guys to maybe step back and just big picture question. Intelligence, how the brain computes it, what that even is. These are Nobel Prize questions in the natural sciences and the greatest engineering challenge in our history. And I think it'd be nice if we could figure out how to leverage in all the expertise. Every talk I'm looking at, I see inklings of what might be going on in the brain. And some of you have mentioned even tools to simulate what's going on. I've heard that mentioned. That's a lot of the activity here in the department is, we see opportunities to simulate what's going on. And rather than thinking, I sort of appreciated that it's become a bit of, AI equals deep learning. How do we implement that in hardware? And that's a very narrow view that seems to be kind of dominating where people are being pulled, and I understand that as economic forces, But it would be good to figure out how we at the university can step out of that narrow view to support the larger view of, hey, what's the next generation of this even going to look like? And I'm not asking for, this is not going to be coming only from all of you, right? This is really, again, a bigger challenge, and I can't put it all on you, but sort of figuring out how to enable those forces together is kind of what the quest is about and really what this workshop is about. So that's not really a question, but maybe a call to motivation, and maybe you guys want to comment on that in particular.
I want to comment on this. The neuroscience community is very good in describing things, and, right? And for different components level and all that stuff, but they don't tell me what it means, right? They don't tell me how it all fits together in the kind of a algorithmic point of view, right? And I think this is one of the major shortcomings that maybe it's a training issue, maybe they are not aware, maybe they
Or it could just be a hard problem.
That's a hard problem. A hard problem. This is a cheap excuse, right? If you know what the problem is and it's worthwhile to solve it, you are at it, right? But when I
seeming to imply though that people aren't trying to solve the problem.
Yeah, but I haven't seen anything. Most of the stuff that comes from the biologically oriented community is on a description level. And it's hard to find the description, to prepare the data, to isolate it and see what's going on. I completely get it, right? But the next step is, what is really the underlying data flow there? What happens here?
So can I suggest, so for example, right, this is, let's say we have connectomics. There are big, well-funded programs to try to figure out all the connections in our brain, but that's not ready yet. Let's take C. elegans, right? What about the Quest implements the graph of C. elegans and lets students put different devices in there, and set different rules and just play, right? Because already that, it's emergent. So when things emerge, you don't always understand why they emerged, but at least you have a model system, right? You can let physicists do scaling analysis. You can let people calculate the power budget. Did you have a more power efficient worm with your memristor than with this synapse that is biological, and so forth. I mean, we lack a playground, and such a playground is a way for different scientists to talk to each other. And I think that's one thing which maybe we could do together.
Model system.
So, model system, right.
I want to just come back to this because I think that the criticism that you raise is a very important one. And I think that there is a lot of neuroscience that is descriptive, and I think there's a reason for that because there is a lot to describe in the brain. But I think neuroscience in the last decade or two has gradually become increasingly driven by the desire of people to explain what's really happening at an engineering level and to really understand how those circuits work, or at least understand how they emerge during development and how they're trained by the data that they get to do their job. So I think your criticism is valid, but I think there's an increasingly big part of the neuroscience effort that's dominated by the desire to do exactly what you're suggesting. There are cases where we're beginning to get some inklings as to how these things work, but we don't really have most of those questions answered yet.
And you can think of the activity right now, I think of it as engineering, forward engineering within the constraint space of the measurement. So you're never going to measure the brain and it's going to hand you a blueprint of what to build. We need people building things on the engineering side within the constraints of the measurement. So the C. elegans is an exact suggestion here, is like when you're providing the constraints, then engineers working within those constraints then discover things, right? That's the spirit of what, again, we're trying to do with the Quest, is to have both of those. You can't do it alone from brain science, but you maybe can't do it alone from just engineering without guidance. So
this is exactly true. Right? If we want to make progress, we cannot do it alone. You guys cannot do it alone.
Right, that's right.
Right? And this is where the interface stuff comes in. You're part of the layer that has to talk to each other. Right? This is, I mean,
we should talk to each other.
Yeah, talk to this guy.
Okay, so for the sake of time, let's take one more question from the audience. There was, okay.
Well, so one thing I'm hearing in common is that sometimes there isn't a shared language for these different fields. I think that was a big part of what I heard in the keynote, is that sometimes people aren't talking because there's not a shared language. And I'm wondering if there's any thought that anyone has, given that we're in a university setting, to help encourage people to speak more in technical terms that are cross-disciplinary.
Yeah, maybe I can add something to that. So I mean, if we think about materials and brain, then there's some language sets they share. So for instance, you could model some of the processes by equivalent circuit models that share actually information on the time spans, on the dynamics that you have in the system. And you can use, I think, the same models that you have in electric engineering, also I think in some of the brain models. And also to mimic different materials and processes. And that can, I think, form a quite strong basis then to look later actually on how to program that and how to speak actually to people developing algorithms more, right? And so I think a part is shared. It's not that not all is not shared, but maybe we have to get together more in developing roadmaps on what we take out of that from materials, different kind of like physics and chemistry you can drive, and then later coming to more complicated networks.
And we should all talk often.
High five. Answer has to be
Good one more to answer.
English will be fine.
I mean, I think there's some joint degrees, right? Like at least for, I know there's something with like Core 6 and Brain and Cognitive Science, so I think that's what I heard.
Yeah.
So I think that they're trying to build these bridges so that students can get joint degrees across these disciplines. I think we have to grow our own people to top grades. That's kind of basically I'm sure that's part of the College of Computing initiative, something related to that, but I don't know the details.
All right. Yeah, let's thank to our panelists.
Jeehwan, thank you for organizing this discussion. I think this was an awesome discussion. I had a lot of really key insights. It was live, and many people want to meet each other.